Let's look at the inductors. An inductor is basically a coil of inductance L. If you have a current here I, then there's a voltage V, and the relationship is V equal L di per dt. That's the basic law which comes from Faraday's law of an inductor. Okay? So if we integrate, we get L di. Integration. The integration of LDI, okay, will give you Li. Integration of V dt will give you flux from Faraday's law. You know that flux, Faraday's law, is called change of V dt. So, okay, no, this is the reverse. The voltage, Faraday's law, is change of flux with dt. So if you integrate V dt, you'll get total flux. Okay? So this is basically the relationship between a current and a flux, which means that if we have an inductance of inductance L equal inductance, the units is in Henry, okay, or H. So if we have a coil of inductance L and we pass a current through that inductor of I value I amps, then we are creating a flux. In this conductor, we create a flux. The value of the flux L times I. Okay, so that is the basics of the inductor. Similar to the capacitors, an inductor will not dissipate energy. It will store energy, but it will store it as a magnetic field. So inductors stores energy as magnetic field. Capacitor will store energy as electric field, while inductor stores energy as a magnetic field. Now we want to calculate that energy. Energy stored is VI dt, and we integrate. Always in any electrical element, we want to calculate the energy. You multiply V times I, which will give you power. This is power. And you integrate that power with dt, will give you the total energy stored. Now, integration. V is L di per dt. I dt. So this will be integration of Li di. So this will be half Li squared. So the total energy stored in an inductor is equal half times L times the current passing through it squared. Okay? Let's look at the connections of inductors. How we connect an inductors. Again, we have series and parallel connections. Inductor connections. Series and parallel. Okay? We have two connections. Let's look at first the series connection. Series connection means we have several inductors, L1, L2, Lx, Ln, okay, where we have our single voltage source and we have a current I. So the current passes through L1 is the same current passing through L2, through Lx, that's why they are connected in series. Again, if we apply KVL, okay, applying Kirchhoff's voltage law, we get V equal V1 plus V2 plus Vn. Well, this is plus minus V1, this is plus minus V2. So V1 is the voltage across inductor 1. Now we transform this to a total inductance, L total, where we have I passing through that inductor. V is equal L total di per dt. Similarly equal V1, which is L1 di per dt. It's the same. The current passing through inductor 1 or coil 1 is the same of that current passing through L total and L2 and so on, plus then L2 di per dt plus Ln di per dt. So this will give you L total equal the sum of all of them, similar to the resistors, Ln, or L total equal sum of L of Lj from j equal 1 to n. Okay, so if we have inductors connected in series, then we add them to give you the total inductance. Let's look at the parallel case, parallel connection. In parallel connection, all inductors should be connected across the same voltage source. So we have L1 here, Lx here, Ln here are connected between two nodes. Okay, so what we have here, I total equal the sum of I1 plus Ix plus In. So I total equal I1 plus I2 plus In. In fact, what we have applied here, apply Kirchhoff's current law. So apply Kirchhoff's current law to this node, we'll get I total equal I1 plus I2 plus Ix plus In. Okay. Now, based on this, what is I total here? If we look at the basic law, that I total, we know that flux equal L times I. Okay. Which means that I equal flux divided by L. So we apply this to here. So I total equal flux divided by L total equal I1 flux divided by L1. Actually, it should be flux 1 divided, but flux 1, note that flux total equal flux 1 equal flux 2 equal flux m. So fluxes will be the same. Why? Because they are connected in parallel, and based on the relationship just I told you about Faraday's law, V equal change over flux. And we have the same voltage here, V across all the parallel elements, which means the magnetic flux should be the same because they are connected in parallel. Okay? Very good. So if we apply this to this equation here, we apply it to this equation, we get flux over L total equal flux over L1 plus flux over L2, okay, plus flux over Ln. So we get 1 over L total equals sum over 1 over Ljj equal 1 to L, which is 1 over L1 plus 1 over L2 plus, and so on. Okay? So that's the parallel connection. It's the opposite of the capacitors. Let's take an example before we end the inductors. Let's take an example. Let's have two inductors connected in parallel and with one connected in series. Let's have here 30 millihenry and here 60 millihenry, and let's have here 40 millihenry. Okay, and we want to calculate L total, so we transform this to L total. Okay, first we look at these two far end. Both are parallel, so we convert them to Lx. These two nodes here, the same as these two nodes here, then connected with 40 millihenry. Okay, let's calculate Lx. Lx is the 60 parallel with the 30, which means 1 over Lx equal 1 over 60 plus 1 over 30, which is equal 60 times 30, 60 plus 30, 90. Okay? Which means that Lx equal 30 times 60 divided by 20. Okay? So it will be 20 millihenry, same units. Okay? Now, Lx and 40 millihenry are connected in series. So that will give you L total. Okay? So L total will be Lx plus 40, which is 20 plus 40. So it will be 60 millihenry. Okay? If a current of 6 ampere passes through the 40 millihenry, determine the stored energy and magnetic fluxes. Okay, we want to calculate magnetic fluxes as stored energy and all these. Now, we have here 6 amps. I equals 6 amps. So the same I here, I equals 6 amps. The same current here, I equal 6 amps. So this 6 amps passes through 40 millihenry. It means it passes through Lx. And here also we have I equal 40 millihenry. Sorry, 40. I equal 6 amps. Okay. So we know the current is 6 amps. We know the L total. We can calculate what is the flex. L total is equal L total times I. L total is 60 millihenry times 10 to the minus 3. We convert this millihenry to henries and times the amps, which is 6. So it will be 36 times 10 to the minus 3. So it will be 0.36. The units of flux is Weber. Okay. So we know that. we know now we know what is the flux of L total. Okay. Now, we can determine also the flux of the 40 millihenry. Okay. So what is flux of 40 millihenry is equal simply L 40 millihenry minus 3 times Li, which is 6 amps. Okay, so that will be 0.24 Weber. 6 times 4 is 24. So 240 divided by 1000.24. Okay. Now, what we want to calculate the fluxes of each one. They are connected in parallel. The 60 and 30 are connected in parallel, which means they have the same flux. Okay? So we say simply, well, this is very important to keep in mind. Okay? We say that 30 millihenry and 60 millihenry are connected in parallel. Now, because they are connected in parallel, it means flux 30 millihenry is equal to flux 60 millihenry is equal to flux X or Lx. Okay, which is equal, we have calculated. We did not calculate that, but we can calculate it, no problem. Okay. Flux in the if we take this, conductors. You just follow very basic rules. 60 millihenry, 30 millihenry, and the current passing here 6 amps, and we know we have converted that to Lx, which is equal to 20 millihenry, and the same current passing through it 6 amps. So we can calculate what is flux Lx equal 20 times 10 to the minus 3 times the current passing through it, which is times 6. So it will be 12.12 Weber. Right. And this is equal to flux 30 millihenry and equal to flux 60 millihenry. Okay? So we know the fluxes. Okay, we want to calculate what is the current. What is I1? What is I2? Now, I1 is equal flex 60 millihenry divided by the 16 millihenry, because flex equal L times I. So we can calculate I. So flex is, we have calculated 0.12 Weber divided by 60 times 10 to the minus 3, which is equal 0.12 times 10 to the power of 3 divided by 60. So it's equal what? 120, right? Divided by 60 will be what? 2 amps? 2 amps, right? We can calculate I2 equal flex 30 millihenry divided by the 30 millihenry. The flex is 0.12 divided by 30 times 10 to the minus 3, so it will be 120 divided by 30. It will be 4 amps. Okay? Okay, note that I1 plus I2 is equal 2 amps plus 4 equals 6 amps equal I total. So what we have here, 6 amps will be distributed to I1 and I2. I1 is 2 amps and I2 is 4 amps. And you calculate them using the standard procedure, so you don't do mistakes. Okay. Now what is left is the energy. What is the energy stored in the 40 millihenry? 40 millihenry. So I have times L 40 times 10 to the minus 3 times the current, which is 6 squared. And the energy stored in the 30 millihenry is equal half times 30 times 10 to the minus 3 times the current passing through it. 30 millihenry, we have calculated that, which is I2, which is 4 amps. So it is 4 squared. And the energy in the 60 millihenry equal half times 60 times 10 to the minus 3 times the current in the 60 millihenry. We have calculated that current, which is I1, which is 2 then squared. Okay, so this will give you in joule, joule, joule. And if you add them, adding, let's say this is W1, W2, W3, adding W1 plus W2 plus W3 must equal, a question mark, must equal to have L total I squared, which is equal to half L total. We have calculated 60, 20 plus 40, 60. We go back to L total, that's L total 60. Passing through that, L total 6 amps. So this is half times 60 times 10 to the minus 3. Okay? Times 6 squared joule. If we are correct in the calculations, we add this and this and this, you should obtain this one. Okay? So this ends up this short video clip of the conductors. Let's continue on the summarize. Let's summarize or summary. Now we have a capacitor, then we have Q equals C times V. We have I equals C dV per dt, and we have stored energy half CV squared. Okay? And we have an inductor L, and this is C plus minus V. And here we have I, then plus minus V, and here also we have I or Q, then V here is called LdI per dt, flux equal Li, and stored energies have Li squared. So this is basically a summary of what we have done, okay? Now, an important note I want you to note, now we will deal with inductance and capacitors in both DC and AC, but now let's emphasize the DC, and later on we'll go to AC when we come to deal with AC circuits. Now, let's see, what is capacitors and inductors and direct current, direct current. When we say direct current, what we mean about direct current, that the current and the voltage V and I are constant time, i.e. V and I are constants in DC. So if we have a DC circuit, the voltage and the current are not functions of time, they are constant. So a capacitor plus minus V in DC circuit, I equal C dV per dt. Because V is constant, means it doesn't change. So this will be I equal 0. Okay? Which means that this capacitor will be an open circuit. Open circuit. We call this open circuit. Okay? We have open circuit means we have no current, but we have a voltage. No current, but we have a voltage. Okay? So if we have a capacitor in a DC circuit, it will act as an open circuit. It has a voltage, but there is no current. While an inductor plus minus V. Here I equals 0. Here L. Here plus minus V equals 0. Here I. Why? Because V equal L di per dt. Since I is constant, this will be 0. So equal V equals 0. Okay? So a zero voltage will act as we have a short circuit. Short circuit means a resistor of 0. We call it short circuit. Okay? Short circuit. Okay? Short circuit means we have an I, but V equal 0. So if we have an inductor in a DC, it means a short circuit, we have a current, but we don't have a voltage. The voltage is 0. While if we have a capacitor, we don't have a current. I equals 0, here I equals 0, but we have a voltage. Okay, that's the main difference. And we will see how we treat these capacitors and inductors if we have them in a DC circuit containing some resistors. And that will be the another video click, okay? So let's do that in a separate video click. Okay, so I'll talk to you later.